Hello, everyone, my dear student and chem lovers. So now we are moving towards the carboxylic acids, reactivity, and their behavior and their chemical properties. So basically, in our previous lecture, we discussed about the structure, bonding, and nomenclature of carboxylic acids. And in this lecture, we are going to discuss about the acidity, because as the name states, the carboxylic acids represent the class of the organic compounds which are acidic in nature. So we will discuss and we will see how significant is that acidic behavior of carboxylic acids is, and where they lie and where they stand if we compare the acidity of the other functional groups versus the carboxylic acid. So let's start. So acidity, they are the Arrhenius, Lewis, and Bronsted definition of acidity, and how we can define a molecule, a compound, if that is an acidic one or a basic one. So visually, and what how we can see that we do the pH paper, we can see through the pH papers on the pH scale that where the pH stands for the solution, or that compound, if it is on the acidic side, if this is between 0 to 5, so this is more this is an acidic band, and then from 6 to 7, this is going towards the neutralization, and exactly 7, this is the neutral point. Then exceeding from the 7 up to the 14, this is creating the basic one. By definition, the molecule which are adding on, which are increasing the hydrogen ion concentration in a solution, and they can liberate in their ionization form, they can give off the hydrogen ion, so they are the acidic one. So carboxylic acids, when we compare it overall and generally, without the boundary of the organic and inorganic, so keeping all the compounds, organic and inorganic, carboxylic acids are weak acids. So the value of Ka for most unsubstituted aliphatic and aromatic carboxylic acids fall within the range 10 to power minus 4 to 10 to power minus 5. So what the Ka means. So as a chemistry student, and if you are still have don't have that idea that what the Ka, so Ka is basically the dissociation constant, the rate of dissociation constant. Whenever we are writing any chemical equation, so from one reactant, whatever the reaction is, so it is converting into the product. So here in this particular case, you can see that this is the acetic acid, and in its solution with the water, so this is converting into the acetate anion, and there is the hydronium ion. So hydronium ion can be written as, you can write it as H positive. So when this extra positive is making a bond with an oxygen, so we do it in a combined form to balance the equation, that this is the hydronium ion, right? So basically, when there is a rate of conversion from the reactant to the product, so when we write the equation that the concentration of the each product, then divided by the concentration of the original reactant, so this is giving us the rate of reaction. But right now this is not reacting with any of the other reactant species, so this is dissociating. This is a ionization type of reaction, that this is from its original, it is converting into its ionic form. So here this ionic form is called as conjugate base of that acid, right? And there is the acidic, which is because that can again, if we move into the backward direction, so this will liberate the H positive ion and the H2O, right? So Ka is basically the dissociation constant, or the of acid. So how readily how fastly and how conveniently a molecule, an acid, can dissociate into its dissociation form, and it can generate its conjugate base and H positive ion. So the Ka faster or the higher the value of the Ka means that there is a higher a dissociation of an acid. So it means higher amount, higher concentration of the H positive ion. So it means higher Ka values give us the hint or indication for the acid strength of a molecule or a compound. Now there is a term pKa. So pKa is basically the reverse of a Ka, or you can say in a mathematical term, this is a negative log of Ka. And if you just take the negative log or inverse log of inverse of this, so then this is the 4.76. So if higher the values of the pKa, more than the 4, or right now we are talking about organic compounds, some of the inorganic compounds do have less than the 4, but right now we are taking acetic acid as a standard, right? And its pKa value is 4.76. So if the pK value is exceeding, then the 4, 5, 6, 7, and up to 8 or 12 or 16. So it means the acidic character is decreasing. It means there is less dissociation, rate of dissociation of an acid. So less dissociation rate of an acid means that this is not giving that amount of concentration of the hydrogen ion, right? Or H positive. So if we just compare the carboxylic acids versus alcohol, so they both belongs to the acidic class of a compound. Carboxylic acids pK value is in range 4 to 5, while in alcohols this is in 16 to 18. So as I said, the pKa is inverse proportional to the acidity or the acidic strength. So it means if the alcohols are showing the higher values of the pKa, it means they are less acidic as compared to the carboxylic acid. So that's state about the pK values and their numerical values. So basically, behind that, what is the logic? So basically, there are some factors which are affecting the acidic character of the carboxylic acids or any of the organic compounds, other functional groups. So this is the delocalization of the negative charge and the electron withdrawing inductive effect. So these are the factors which influence, which either enhance the presence of these enhance the acidic factor. So if we just talk about the carboxylic acid and we are comparing with the alcohol, in alcohol the functional group is OH. So there is one oxygen which is directly linked with the hydrogen from one side and the R group on another side. And the carboxylic acid is a class where we have the carbonyl, where there we have the OH. Now the carbonyl functionality is such an significant functionality that it has the ability to delocalize the electron around the carbonyl oxygen, and in nature this is basically electron withdrawing group and its inductive effect is electron withdrawing. So that's why these enhanced features are making carboxylic acids more acidic as compared to the alcohols, because alcohol don't have that resonance ability of around the carboxylate ion, because there is no carbonyl in that way, and then there is the methyl group which is attached, or the R group which is attached, which is not having the electron withdrawing ability as an inductive effect, right? So these are the things which are making and which are contributing in the stabilization of the carboxylate ion and making this more stronger one, right? So in other alkoxide ions, you will not see that much resonance or inductive effect stabilization as you can see in the carboxylic acids. Now we'll see the effect of halogen substitution on acidity. So basically, I have used the term inductive effect. So inductive effect is basically the polarization and the charge induction created by the presence of electronegative element. So if a group which is highly electronegative in nature and that has a tendency to drift that electron density towards itself, so this is making its counterpart as electropositive one, right? So we will see how that this is influencing. Right now, straightly we will compare the four cases, that how the presence of halogen substitution is influencing directly on their pK values. Right now we are comparing in terms of numerical values in a pK, but in the next slide I will show you that how this is for creating the resonance stabilization and the delocalization of electron, which is contributing for the higher acidity of the carboxylic acid. So halogen are the elements which are electron withdrawing in nature. So their inductive effect is -I. So we have set up this, that in electron withdrawing group has a positive impact on the acidity one. So right now we are comparing the different versions of acetic acid with the 1 chloro substitution, 2 chloro substitution, and 3 chloro substitution. So if you just see the acetic acid, its pK values is 4.76. Now, if we substitute 1 chlorine here, so this is a chloroacetic acid, and you can see that pK value turns to 2.86. Now, when the 2 chlorine atoms have substituted, so this is a dichloroacetic acid, and the pK value reduced to 1.48. Now the trichloroacetic acid is 0.70. So what you get out of it? So I have told you that the pKa is inversely proportional to the acidic strength. So it means higher the pK value, um, the weaker the acid as compared to the other one which is having the lower pK value. So in these four scenarios, if you have to arrange them in an increasing order, so that is the straight forward, where this pink arrow is showing the acid strength. So the weakest among these four is the acetic acid, and the most strongest acid is the trichloroacetic acid. Now, I will mention you that how this inductive effect is participating in stabilizing the molecule and the carboxylate when we are adding on chlorine, right? So the polarization of the electron density of a covalent bond caused by the electronegativity of a nearby atom is basically the inductive effect. So here you can see this is the chloroacetic acid. So the carbonyl oxygen has the ability that these pi electron can delocalize. Then this negative charge, which was formed by the dissociation of the chloroacetic acid, is that it can build up the double bond. So they are in constant delocalization and in the movement. So that's why this is equally distributed. Sometimes this is in a double bond, sometimes this is in a double bond, and this is with the negative charge. Now, if we just ignore that this chlorine is not there, so there is only the hydrogen. So it means this carbon and hydrogen, their bond is not the polar covalent bond, right? Right. So there is no such strength of positive bond. So the electronegative charge is concentrated on this oxygen, and this is not as a stable entity, because the all of the negative charge has just concentrated on this side, and nothing is there to counterbalance this one. But when we have added the 1 chlorine here, so this chlorine has made this covalent bond the polar one. So the carbon is getting partial positive, and the chlorine is, of course, the partial negative one. So this extra positive charge which has created on this carbon is basically to neutralize the negative charge on the oxygen. But if that is not a positive one, so that means that is just the one side which is getting the negative, and the rest is just the neutral one. So this is not creating that symmetry and stabilization. So that's why this chlorine making this carbon electropositive partial positive, which neutralizing this negative charge, and this negative charge is distributed equally between the two oxygen. So this dotted line is to show that these pi electrons are in a movement. So sometimes has formed and then this break. So this is not the solid one, that not fixed, that only this carbonyl will be in the double form or this carbonyl will be in the double form. So this is keep on moving. So I can just use the arrows to mention you that this negative can here can be there, right? So that will be moved there, right? So it means now this is in its another resonating form, that this is now in a double form, double bond with the carbon, and now this oxygen is in ionized form. Here this is another example. So to make it more elaborate for you is that this is the trichloroacetic acid, and again this is its ionized form, and there is the hydronium. So now you can compare. Right now we have added the 3 chlorine atoms in it. So it means that these chlorine are covering the all sides of this carbon. So it means this negative charge is spread the negative charge onto the chlorine atom, making this carbon highly partial positive as compared to the previous one. So now this negative charge can be neutralized with the impact of these chlorine. So that's why this trichloroacetic acid is more stronger as compared to the chloroacetic acid. Now there is another case of the inductive effect. So whenever we have the double or the triple bond, they also have the electron withdrawing inductive effect. So here this is the benzene ring, which is in itself is in the sp hybridized carbon bonding. So that's why this is providing also the good electron withdrawing species or the moiety. So that is again making this carbon partial positive, right? And this carbonyl of course is in the delocalization, and that can take up drift that electron density towards itself, and that can also do that due to this benzene ring. So these are stabilized because of the presence of this phenyl ring or the benzene ring. So unlike this methyl one, because this methyl is a smaller one and there is no polarity between the carbon and the hydrogen one, and so this conjugate base or this anion form will not be stabilized by the second carbon, the neighborhood carbon of the carbonyl one, while it do in case of the benzoic acid. So if you just see the benzoic acid pK value, it is 4.19 and acetic acid is 4.76. So it means acetic acid has the higher pK value than the benzoic acid. So it means acetic acid is the weaker as compared to the benzoic acid. Now there comes a checkpoint quiz just to ensure that you get the difference between the substitution of the electronegative and electron withdrawing groups on the carboxylic acid and how they impact. So you have to answer these, and I would like if you comment and you just share your answer just under this lecture on YouTube channel. So after getting the maximum of your responses, then I will share the exact answers so you can check that either you were at the right point or not. So basically the hint I will give you that you have to see that where there is a substitution of electron withdrawing group. So you can check out, you can Google, you can refer to any book where you will find out the list of electron withdrawing groups. So hydroxyl, ammonia, nitro, halogen. So they are the different groups and elements or the group of atoms which are the electron withdrawing group. So we have established that what is a reality, what is the effect of electron withdrawing group on the acidity. Now the second part is this one. Here the hint is this, that when there is a atom or element which is attached to um, some of the acidic side, that this is having the higher in size, and it means a negative charge can be spread on the larger volume. So it is also helpful for stabilizing the charge distribution and to make that conjugate base more stable. So if you just compare the acetic acid and sulfonic acid, so do keep in your mind the difference between the size of the oxygen and the sulfur, and you will get the right answer. So next is the solubility of carboxylic acid. So though the carboxylic acids are having the polar covalent bond, but if we are keep on increasing the R chain, and then the aromatic ones, so they are mostly not soluble in aqueous medium, or they have very less solubility in the aqueous solution. So the solubility of carboxylic acid is very much dependent on the pH, because the pH is providing the tool that either you can play with your carboxylic acid to either to make it soluble in your aqueous solution or not, by adding some of the basic or the acidic solution. So generally what is a rule is that at the pH, which is a very acidic one, 2 or less, the carboxylic acid do exist in its fully undissociated form, in its fully protonated form, as we have discussed in the case of the amino acids also, because there is a higher number of the H positive ions. So whatever the anionic form will be generated, so they can capture that H positive and they can convert into its undissociated form. When the pH, this is an interesting point, that when the pH of that solution is equal to the pKa of the acid, so then that acid will exist in its both form, and it's in equal amount concentration of their both forms, unionized and the ionized form. So this acid, let's say if we say this is the acetic acid, so this is the acetic acid, this is the acetate anion. So they do exist in equal concentration if we have maintained the pH of the solution around the 4.5 to 5, because its pK value is 4.75. So if the pH exceeding the 7 or it is equal to 7, then the predominant species which is existing in a solution is its ionized form, because obviously there is the OH ion which can capture that hydrogen positive. So the predominant is this one. So right now I haven't wrote this, that this is exactly the ionized, and this is fully the ionized form. So this is the predominant, means this is higher and this is larger in amount. This is not the case that it is 100% in that form, but the larger one is this one, because that is the predominant form. So the reaction will proceed in that direction, where this is which form is favoring for that pH condition of that solution. Now, as that fact has established so far that the carboxylic acids are good acidic groups or compounds, so it means they can simply react with the base and they can generate the salt, because from our general chemistry and our basic chemistry, we know when the acids and bases are mixing together, so they the net result is a salt and the water molecule. So same is for the carboxylic acid, but obviously the acids are not the salts are not as simple as we do in the inorganic or in a basic examples. So all carboxylic acids, whether they are soluble in aqueous solution or not, so they do react with the bases sodium hydroxide, potassium hydroxide, sodium carbonate, sodium bicarbonate, to form water soluble salt. So it is very helpful sometimes, because when we are looking for a product that we can filter it off, or it is very helpful in a drug designing else also, because whenever we have a product and it has a carboxylate side, but definitely this is not soluble in our aqueous medium, so this is incorporated, it is formulated in a form that we develop their salt. So maybe if you just have seen some of the flare or uh, um, the description or the detail paper in any of the tablet or your drug box, so you can see that most of the drugs are in a salt formation. So this is in a salt formation because they are then visible for dissolve in an aqueous medium, because in our body system there is the aqueous, there are fluid and hydrophilic, and there are the lipid also. So that is soluble to penetrate some of these ion channels, and then for the lipids and to pass out the membrane, then it resume its organic form. So then it can be the part of the organic um, fluids. So the benzoic acid, when react the sodium hydroxide, so this convert into the sodium salt of the benzoic acid. So how we write that name is the sodium benzoate. So I hope you get why we are writing the 8 for this one, because this entity or this species is now again giving you the resemblance that how which class of the organic compound it is, R, then the carboxylate side, and there is another R. But right now this R is basically replaced with the metal, any group of atom or inorganic group, but the sandwich point or the functionality is the same one. So this is presenting the version of the ester. So this ester, the esters, we use the suffix ate. So how we name the salts of these carboxylic acid is that out of this we get this ester functionality surrounded by from the both side. So we write this inorganic side as a prefix, and then whichever is the contributing side of the carboxylate is as a parent name. So this is the benzene here. So right now we will see the benzo, and there's 8 for this group, right? So in a similar way, we will name this if that benzoic acid has reacted with ammonia. So then it has made ammonium benzoate. So you can see that the benzoic acid is slightly soluble in water, and when we convert it into the salt of these, so its solubility has increased so far that in case of the sodium salt, it is a 60 gram per 100 ml of water. And if we have the ammonium salt of the benzoic acid, so then this is a 20 gram per 100 ml. That's again not bad. So from the very slight solubility, we are converting them to the highly soluble and considerably soluble compounds. So that is the edge of that acidic behavior of the carboxylic acids. Now, another very famous and a very interesting reaction, which the students really enjoy in the chemistry lab, is effervescence test. And that is the conformity test for the functional group of carboxylic acid. So when we do the compound detection and we have to find out the functional group detection, so we do perform these ones. So firstly, when we check the pH, so alcohol and carboxylic acid both show the acidic behavior. So now there is a question that what we have to write in our inference, that either the given compound has the alcohol functionality or the carboxylate. So then there is a test that we do react the carboxylic acid solution with the sodium bicarbonate and the sodium carbonate to form the water soluble sodium salt, right? So as a result of this reaction, what is happening, that there is the formation of carbonic acid, which eventually decompose to give the carbon dioxide and the water. And this carbon dioxide, basically, when it evolves from the solution, this is creating the bubbles. And the sodium bicarbonate is a source of this, but of course, it can't happen if it is not reacting with the carboxylic acid. So if the group is a carboxylic acid, then this is facilitating this one, that this is taking up this sodium part of this one and making the salt water soluble, and then there is a carbonic acid which will eventually convert into carbon dioxide and the water. So canceling the same species from the both equation, which are the common one. So the net equation is the, by writing uncommon from the all sides of the equation. So this is acetic acid reacting with the sodium bicarbonate, and we have the sodium acetate, and there is a carbon dioxide, and there is a water molecule. By using the acidic nature of the carboxylic acid, we can separate the two organic acids by the solvent extraction method. So usually in some of the lab exams, your instructors and advisors do ask you that if you have a combination or mixture of an alcohol and carboxylic acid, how do you separate these by using the solvent extraction? So you have to use your chemistry here, and the knowledge about the carboxylic acid is that how smartly you can treat that solution, so you can get out of, and you can separate these both components of the mixture. So right now in a benzyl alcohol and benzoic acid, so if you just look at these structures, so these are purely organic, and they can easily soluble in any of the organic solvent. And if we dissolve these in a water, so they both are insoluble, right? So what we'll do is, so obviously for the solvent extraction method, there should be the two immiscible solvents, and the one component has to be the part of organic layer, and another one has to be water. So we can separate the both layer, and we can recover the dissolved compounds in it to get our product. So firstly, what we will do is that we will dissolve this mixture in the diethyl ether, which is organic solvent, and this is a very low boiling solvent, so that's why we are using that one. The second is step is that we will treat that mixture with the 0.1 molar aqueous solution of the sodium hydroxide, and we will shake this and we will mix it, and we will see the two layers. So now in these two layers, in the ether layer, the benzyl alcohol is there, because benzyl alcohol is not that strong acid that it can make the salt with the sodium hydroxide, while the benzoic acid do form the salt with the sodium hydroxide. So it means that has converted into the water soluble sodium benzoate, and the benzyl alcohol is in its as such form, and that is in ether layer. So by distill uh, of the ether, we will get the benzyl alcohol, or we can do perform the rotavap also. So at the distillation, we will recover the both liquid at their different boiling points. So definitely diethyl ether has a very low boiling point, so that will be separate out firstly, and we will get at the end the benzyl alcohol. Now we get that sodium benzoate. Now from the water, this had to distill it off, and so the better thing is now there is the most efficient thing is that we can convert that product into water insoluble, and we can just filter it off. So now we don't have to go for the distillation or the rotavap. So what we do is that we will acidify the solution with the same strength of the base we have used, 0.1 molar HCl, to neutralize that effect of the base. And what will happen to the sodium benzoate, that it will convert into the benzoic acid and sodium chloride. So sodium chloride will be the part of that aqueous solution, and it will dissolve in it, and the benzoic acid will be the insoluble material, and that will settle as a solid, so we can just filter it out, and that solid product is the benzoic acid. So how pretty it is. So you can use acidic behavior of the carboxylic acid for planning your workup, for setting up your reaction, which solvent you have to use, and how you can react the different other reactants with the carboxylic acid to get your desired product. So in future, we will talk about more about their other reactions. So it's for today. Thank you so much. Have a good day.